For our last talk of the mini school, we're very happy to have Andrei Okounkov from Columbia, who will talk about Gromov-Witten theory and representation theory.
Well, thanks so much. I realize it's been a long day for everybody. I'll try to, and honestly, what I was going to talk about will require a whole new set of ideas, in addition to what's been introduced already. So, so we might as well go slow because. So what's representation theory? Am I going to write this up? So it's hard. I mean, this is a question often. People often ask this question in context of like qualifying exams, and so whatever representation theory is, it certainly should include finite-dimensional representation theory of semi-simple Lie algebras. So, like, I was going to write this because it's going to be a recurring theme. So it's like universal developing of some Lie algebra G going to matrices of some size n over some field. And geometric representation theory starts by trying to think about either the source or the target of this map somehow more geometrically. And so, well, let's start with the target. So what are matrices of size n? So, okay, so think about matrices of size n. We can think of this as with whatever coefficients here, this coefficient cohomology with the same coefficients of x cross x. And where x is a set of n elements. And this acts on an n-dimensional vector space, so this is with coefficients, I don't know, some field, which we denote complex C. It doesn't matter what field is. And so, in this acts on an n-dimensional vector space over that field, which is, of course, cohomology of x itself, by the following rule: if I have an element here, alpha, and an operator, so it's an actual matrix in here, that is going to go to where? So the matrix multiplication, the way you write matrix multiplication is like this. You pull back. So this has two projections to x. So there's P1 and P2 projection. You pull back with the second projection, the class alpha. You cup it with M, and you push it forward to the first projection. And so now this formula, of course, works wherever. So it has to be whatever x, as long as this push forward is, say, proper. So if this map is proper on the support of that class. So this works in cohomology, works in K-theory, works in Chow groups, works wherever. So it means the cohomology of the product acts on the cohomology of individual factor. And this is one way. So if x is, instead of being an endpoint set, is now, and so the elements in here in general, so this is somehow forget about matrices now. So x is general. Elements of this set are called correspondences. And they act. And so one way to think about representation theory geometrically is to try to make a source target of this map geometrical, is to try to map interesting algebras to correspondences. Make them act by correspondence. Generalize acting them by matrices. And where we go, where in enumerative geometry we're going to get interested. And the point of that, of course, I mean, you're not interested in all matrices. You're interested in interesting matrices. And where in geometry we're going to get interesting matrices? Well, we've been looking at interesting matrices the whole day. So if x is slightly, so if x is now some algebraic variety, then I can look, for example, at the moduli space M to 0x bar, some degree beta. This will have two, evaluation map at the two marked points, going to x cross x. And the subject of many, somehow, starting from the very first talk by Jason, we were discussing an element here, the virtual fundamental class. Which, of course, I can then push forward to get an interesting element in homology. Here, well, x is smooth, so homology and homology the same thing. So it's not an element here, it's an element in homology of the space. Too fine a distinction this late in the day. And and for which x is this going to generate, so this is going to be some operator, right? And so for which x can we say something meaningful? So this is, for example, this range is overall beta. So for which x I would expect to say something meaningful about the algebra of operators that this will generate. So we now come to now time to be reminded that there is no, this is attributed to Manin, which I heard from Shurik's father. So this is that there is no such thing as general algebraic variety. So this somehow this well, okay. So if you have to be, it's like, or for that matter, there's no such thing as general group. So you have to be, if you want something interesting, something non-trivial, perhaps you want to perhaps you want to restrict the class of varieties for which you expect something. So right now, this of course exists for any x. But the point is that you'd like to, if you'd like to somehow describe the algebra of the correspondences obtained in reasonable terms, you probably want to restrict the class of x you consider. Otherwise the problem, there's just no language in which to answer that problem. And so the class, the class of varieties that will be. So what the right class of varieties is, it's somehow. So this will appear later when we will talk about the source of the map. So right now we're talking about like some kind of this side. What the really right class of varieties is, maybe it's not clear at the moment, but certainly the good, the interesting. Not making, well, it's also some kind of statement of judgment. No, of course, they're interesting x. That set certainly includes varieties that are called equivariant symplectic resolution. And these are varieties satisfying three conditions. First, they're holomorphic symplectic. Sometimes people assume that symplectic form is like unique. So it's very interesting, easy somehow. So it's a good assumption to make. Second, they're resolution of singularities. That is to say that if I take x and map it to the spectrum of the global functions, which is not x naught, which is spec of global functions on x, I want this map to be projective proper birational. And third, I'd like a group action scale somehow, act on X, scaling. So holomorphic symplectic, there's a symplectic form here in H0 of omega of X. Scaling omega non-trivially. And moreover, you'd like to, so it means, so if this is reductive group, and if it scales omega non-trivially, omega unique up to, let's assume omega unique up to a multiple, therefore it scales it by a character. Reductive group has a character. That means it's a product of some other reductive group and multiplicative group of the field. And usually people assume that this, you'd like this thing to contract, somehow this thing to contract, somehow this thing acts with positive weights. On my variety here. And so what are there are two main examples of this. No, it's actually contract. That's a singular fine variety. And I'd like the whole thing to contract to one point. This is.
So X naught only has one singular point.
X not singular.
No,
but X naught has many singular points, but there's one to which it's it's like a cone over
the most singular point.
The most singular point, yeah. So examples. Well, there's the first example in the business is you take the singular cone. So this is whatever xy equals z square, and you resolve it by blowing up this point, and then the total space. So this is P1, which is I guess there's no consistency. So this is my P1, which is the exceptional fiber that blow up, and the total space is then T star P1, mapping here. Right? That's like the V, and this is the first in the the group action. Well, it's the multiplicative group cross JL SL2. Multiplicative groups SL2 acts as automorphisms of that, and this scales the fibers. And so more general, this fits. This is the first series of examples in two different categories. So this is one set of category is the cotangent bundle of a homogeneous space, or maybe say homogeneous space in general, but maybe take the flag variety. And then the group itself. So this is slightly unfortunate because this is my group G prime. So maybe I'll call G prime here. Because the group G prime acts on this, and also there's another multiplicative group that scales the fibers. And so then this map here is, so this is incidentally this equation. This is the nilpotent cone. In SL2, right? Because if I write the equation that z minus z xy, the determinant of that equals 0, well, I guess with the other sign, I get this. Right? And this maps, but this map here is really, it's just the moment map of this action. So if you just take the moment map, then it's going to go, well, canonically take the moment map. So this will be sitting inside the dual of the Lie algebra. But in fact, the image is going to be the nilpotent cone. And the reason this is nilpotent cone because the group here acts with an open orbit. It's easy to see a group here acts with an open orbit, but it's also scale invariant. So every element in this cone is conjugate to itself being rescaled, and that is definition of being nilpotent. Means the eigenvalue of your operator equals the eigenvalue of 5 times this operator. Means they're all 0. And more generally, if you take G mod P, this will go to some specific closure, some specific limit somehow. And then the second thing is different. I can take the Hilbert scheme of I take a symplectic surface S. This would be a symplectic surface such as, for example, could be just C2 or more general some ADE surface here, and points. And then this maps by the Hilbert-Chow map maps to S to the n mod Sn. This S is not this S. I don't know. This is a symmetric group. Automorphisms of endpoint set. And in particular, if I take the, this thing is singular along the locus where 2 points come together, and the singularity is precisely this cone here. It's also C2 mod plus minus, and that's precisely the singularity of this surface of this singular sorry, not singular surface, of this singular variety has that kind of singularity, and that is resolution. More generally, if you have a symplectic more generally, so this is if this fits inside more general.
That looks like here you don't have a most singular point, you have a most singular stratum where all endpoints are the same.
Right.
So the group is supposed to contract toward that stratum.
Right. I mean, strictly speaking, all of this have, the way I've written, there is a contracting action to the center. But you're right, that center is just this. Here, in this case, for C2, would be any point will be just a singular. But that unique point is. So right, this fits inside. This 2 fits inside. 2 sits inside moduli. More general moduli of shapes on ADE surfaces. And that sits inside more general Nakajima varieties. And this is why, so maybe this is why we're interested in curves. This is why geometers are particularly interested in studying rational curves in these varieties, is because if I have, maybe I'll draw this picture here. So naively, what's a rational curve? So a rational curve, if I want to map from P1 to the Hilbert scheme, say the Hilbert scheme of my surface endpoints, naively it's the same as I have an actual product, so a threefold, which is a product of my surface S with P1, and am I asking for a curve which maps with degree n to P1. This is for a general surface, this would be this type of, this is a Gromov-Witten problem, and could be phrased as a Gromov-Witten problem. For a general, so this would be genus 0 Gromov-Witten. So this is a question, this is genus 0 Gromov-Witten. A problem. that concerns this space, and this is genus higher genus. Yeah. Gromov-Witten problem of threefold. This is two n-fold, and this is threefold. And in general, they're different, but not sure what's happening here. But if the surface is symplectic, that they are the same, and I mean one of the surfaces that's the same, and moreover, it's also the same as something which wasn't exactly mentioned. It's also equal to somehow dt theoretic problem here. And why it's interesting to have, since some of us are really interested in threefolds and in various ways to count curves in threefolds. And in many respects, this turns out to be a very special kind of threefolds for sure, but very important one. And the way to think about representation theoretically about it turns out to be a key to many further developments. And anyway, so now we're going to go back, and what that correspondence I raised, I will just now give you what sort of an answer one gets for this thing. So I remind you that what we were dealing with. We looked at moduli m02 bar x some class beta mapping to x cross x by the evaluation map, and we were interested in pushing forward the virtual fundamental cycle of that. So the first question is, what's the dimension of this object here? So the dimension is the expected dimension. And this is already, the formula already appeared. And so the answer is, well, you start with 3g minus 3 minus 3g. Yeah, 3g minus 3. Bad beginning. So the g is 0 here, so g is 0. Plus the number of marked point, which is 2. Plus, well, I already used the g is 0, so I'll just add dimension x. So in general, there was more general formula Davesh wrote, but just plus, we have to pair c1 of x with beta. And so, so this will come out, those simplifications here. First, this is x is symplectic, so in particular, its first term class is 0, so this thing is gone. All right. So second, this very complicated algebraic expression simplifies to -1. And third is the image of this. The image of this map, it's not just in x cross x, but in fact, it's always in, so these are 2 points that lie on a curve. So when I move, have this affinization, affinization will necessarily contract any curve. Right? So two points that lie on a curve, they will map to the same point in x naught. Right? So this sits inside, in fact, in here. And now for this symplectic resolutions, there's a marvelous general fact that this, in fact, this object is in fact is always Lagrangian subvariety. So this is a product. It's usual when you take the product of symplectic variety with itself, you usually take symplectic form on one and minus the symplectic form on the other. So that, for example, the diagonal is Lagrangian. So this is what I do here. And there's a general fact that this object is always Lagrangian in here. And wouldn't it be nice if this one wasn't there, right? Because then we would see that the image of this class. So if this one wasn't there, we would see that the image of the class will have to be just a union of components of that Lagrangian subvariety. I mean, it's reducible. It's just a union of components with some multiplicities. And so this one is taken out now by the third condition, is that you see if you have a holomorphic symplectic variety, then most of the time, I mean typically, I mean always, its Gromov-Witten variants are just 0 for some stupid reason. And then fortunately, if you're in this situation, while the ordinary, as we discussed, or this kind of thing in ordinary cohomology, that thing is actually 0. In equivariant cohomology, it's not. And in fact, in equivariant cohomology, the fact that it's always divisible, so that thing is always divisible by the weight of, so let's say, non-trivial, let's say, with weight h bar. So actually, if you think of what h bar really means in like Heisenberg commutation relation, h bar is better be not the weight of the symplectic form, but the inverse, or the weight of the Poisson structure. But you know, let's not worry about this now. So this thing is always h bar times something else, some other class which is reduced. And then this expected dimension, this reduced class, then this one goes away. Now I get rid of this one. And so then the reduced class, the image of the reduced class, which just says that this homology class always divisible by that. And so it's really a class of dimension 1 bigger than you hit with this expression. And so that is then a union of components with some numbers. So it's a good beginning. And so it lies. So it lies in something people call like the components of this is what people call Steinberg algebra, because this generates some operator Steinberg considered a million years ago. And so this inside. So if you're in this situation, these are right. So I'm just saying this is Lagrangian in here. Its components generate acting by correspondence Lagrangians, and they mean this sort of thing is closed under convolution for obvious reasons, and so that would be slightly not obvious. Anyway, it's closed. So and they generate some algebra. So that says these images of my operators. Yeah.
So you say that that virtual class is a multiple of some thing that's not reducible anymore, right? So why do you say that the -1 goes away? I don't understand that.
Because this has cohomological degree, right? In homology, it has.
Is that a number or what? I mean, I don't understand.
Well, this weight is h2 homological of a point. Yeah.
Okay.
And so if you create cohomology, the elements of you get right, exactly, yeah. So operators of this kind of enumerative, my enumerative operators. They belong to the Steinberg algebra. And this Steinberg algebra is generated by components of this one. I mean, this is not this is not how we would normally define standard algebra, so I apologize, but so it doesn't agree with the normal definition. But let's for the purpose of this talk, let's call it this. So of this component. And so what this algebra looks roughly for symplectic resolution, you should think that this guy looks a little bit like the structure of this. Should be somehow. I'm not going to axiomatize it in the time given to me, but the way to think about it that this is some algebra which roughly looks like a universal developing of some Lie algebra, but then you take the invariance of the Cartan algebra. So a typical example in here, if this is the algebra you study in introductory representation course, typical example here would be a product of E alpha. E minus alpha. Usually people sometimes denote it F alpha, where alpha is a root and F alpha is like for T star P1. Like for T star P1, what's in so in T star P1. This algebra contains this for T star P1. There are two components there, namely, for my if X is this, then X over X naught. T star P1 was mapping. What was mapping to? It was mapping to this cone, and the preimage of that point was P1 in the zero section. So this has two components, namely it has the diagonal. And P1 cross P1. No, it's not. And the way you think about this operator, you should think of this as being like EF in the two-dimensional representation of SL2. So similarly,
Product of matrix algebras.
Right.
Maybe it's the same content of what you said, but I don't recognize.
What?
Maybe it's the same statement as the invariant under Cartan of UG, but I don't know that language. So, but it is a semi-simple.
Maybe, how to say? Maybe the way to think about it is more like this. This is certainly a very big algebra. It's not matrix algebra. It's not a fine dimensional. And so another example is if you have a Hilbert scheme of points. Say I don't know. Say I know S. And points. Then their operators, well, in cohomology, or just write an operator. So in cohomology, this can go to the Hilbert scheme of let's say surface B, the plane for simply plane. So there are these Nakajima operators that act. So if I have n points here, say 4. This can act a very fat point. If I have a cycle, I can take some point of fatness k running around that cycle. So this would be the cycle gamma. This would be alpha minus k gamma. And so then, this alpha minus k generate Lie algebra, which is GL1 hat, Heisenberg Lie algebra, or several copies of it if the homology of this is more than one-dimensional. And so this is the algebra G. The Cartan part of that measures what the number of points is. And so the elements in here are just expressions in Nakajima operators that have as many creation operators as annihilation operators, like alpha minus k alpha k is an example. And so in this setting, one expresses a very general. If you think of this sort of like this, in this term, there's a very general pattern one expects for the answer, and which is a theorem and somehow the answer. So now I can form that. So let's form a convenient form of generating. Every time you study enumerative question, you always form generating function. So which is going to do now. So it's a sum over all beta q to the beta. As discussed before, this is just an element in the semigroup algebra of effective curves. And I take this evaluation pullback of my reduced virtual class. And so the general pattern was, so this is the theorem. So this is the theorem of Davish and I. Theorem of Davish and I for Nakajima varieties. And so there's a version of this by Chan Zhang here for homogeneous spaces, and one expects a very, there's a similar version for all known symplectic resolutions, but I'll write it for Nakajima varieties. So this is the sum now over roots alpha of that Lie algebra G. I didn't tell you what Lie. So this roots they also sit the roots of some Lie algebra, but also sit, of course, this beta sits in H2 of X roots. These are positive roots. So Z2 Z effective. And this sit in there, that sit in the exact same space. So the roots of this Lie algebra, there are some special curves in X. And then it's log of 1 minus q to the alpha, and then e minus alpha e alpha, which by this you understand this is the invariant tensor. In G minus alpha, G alpha. So there's some Lie algebra with, so this Lie algebra has an invariant bilinear form. That invariant bilinear form puts root spaces of opposite root spaces into duality. Once you have a space and it's dual, then there's a invariant tensor, which is sticking here. And which is you should understand that this is in general, for very general situations, this can be more than one dimensional. There's some Lie algebras here most of you have never seen, and in fact nobody has ever seen because they're kind of very complicated Lie algebras. But this is for Nakajima varieties for JL1 head. What this says the Nakajima operators times the opposite Nakajima operator, and that's the old theorem. And so what that in particular, what this thing implies, something about how once we get to a point So once we get to What was I going to say? Right. And so later in my talk, which of course I realized is, there's not so much time left to say, much later in my talk, but later in my talk I was going to talk about something completely different. But to make connection with what I discussed here, I was going to write down something which is called quantum differential equation. And the quantum differential equation is the following. It's an equation. It's for. Yeah, sure.
Equality. So
yeah.
On that side, you have those E alphas, but you said really they're mapping into the cohomology of the fiber product, right?
Yeah, this is an element in this specific element in this time ecology.
In this, okay. And so Q beta on the other side, Q to the beta is in H2. So alpha, how do we have to think about it? So that the two things can match.
Oh, it is the same thing. Alpha sits. It's just in the Steinberg algebra. You should think of this. These are torus invariant. I mean, the way to think about it is heuristically and rigorously for non-academic varieties, that these are like elements of weight 0 in the universal element of some algebra which is graded by root. So that makes sense. I mean, it just says for every there's some Lie algebra which I didn't tell you what it is.
Roots and H2 of X. So
yes, that is the same. That this is the root lattice. This is the root lattice. This I said that the roots have very specific curves in it. So quantum differential equation is the following. It's the equation. It's an equation of function psi of an argument q. Q sits. So this q is a function on H2 of X with values in the whole cohomology of X. Some people sometimes call it, to belittle this very important equation, sometimes people call this small. But it's pretty big equation. So let's not call it small. It's not technically big either. And so the equation that it satisfies is very simple. So this is, if I want to differentiate it, so you take an element here. This is a function. So sorry, this q to the q is a function in the sense that if I want to differentiate d by d lambda, lambda is a class in here of q to the alpha. The result is pairing alpha with lambda q to the alpha. And so of psi of q, that is lambda times psi. It's a linear ODE. No, so it's not a linear. So it's a linear partial differential equation because you can differentiate in any direction here. And then if you write this out, what this thing means is it gives you an operator which is so this operator lambda star. So maybe I'll this part here. I'll expand on this part. This starts out with the cup product, the operator of cup product, plus, or rather minus, because if we're going to differentiate this thing, it's going to come minus. And this was a reduced class, so there'll be a h bar standing outside. Summation over alpha, q to the alpha, 1 minus q to the alpha, alpha paired with lambda, e minus alpha e alpha. And this is by the divisor equation. So the divisor equation tells you that 2-point invariance, you know 3 points where you insert one divisor. So this applied to my function psi. And you recognize that this is something called Casimir connection. For that Lie algebra G, it's some remarkable flat connection on the Cartan subalgebra of G with values in G. Well, really with values in some kind of big algebra, because this operator, it has some complicated commutation relation with this operator. But this operator is not in my U of G, and it's in something else. So that, but it's And so this now I have 15 minutes to connect this equation to something completely different. It has to do with going back to this and doing something very different about it. And so now we will try to, in the remaining 10 and with a few minutes left, we'll try to do something completely different. We'll like to think about this side more geometrically. And let's go back and think about the G. Let G now forget some Lie algebras you've never seen before. Let G be now finite dimensional semi-simple Lie algebra over complex numbers, or over Z as defined. And so then, if I take UG, that has a center, right? So that has a big center. And if I study representation theory, you might as well mod out if you're interested in your representations. The category of representation is going to decompose into blocks according to what the central character is. If you center X by different eigenvalues, there's no Holmes, no X of any kind between representation where the center X by different eigenvalues. So if I take so that contains a center which is isomorphic to functions on the Cartan subalgebra W invariant. And so if I mod out by somehow what's a character of subalgebra just is a choice of some element here, right? 5 functions on the dual Cartan. So, right, if you have a one-dimensional representation of subalgebra is just choice of a point there, choice of a highest weight, if you want, and so then if I take this by this character of the center, by the central character with the given central character. That is the same as differential operators in sections of this highest weight defines for me a line bundle on the flag variety. Differential operators sections of line bundles defined for fractional line bundles. Because all you need to know is how, if you differentiate, in other words, what you need to know is how to differentiate fractional power of a variable, and that's okay. Right? So what I'm saying is that if I ask, of course the Lie algebra acts by differential operator on G mod B, and these are all equivalent line bundles, and so they act in all of them. And in particular, and if I ask how the center acts, well, the center exactly picks out what the highest weight of that line bundle is, and then the statement is that the whole universal developing acts if the Lie algebra acts by first order differential operator, the whole universal Wellbeing algebra was going to act by all order differential operators. And the statement that in fact that this is so this is what these are global sections of a sheaf of differential operators. So your algebra, which may be slightly complicated, is obtained as global sections of something which is differential operators on all varieties or on non-singular variety. They look more or less the same. And this is kind of an important idea. It goes back to Gelfand and Kirillov, in fact. So I mean, in one way. So Gelfand and Kirillov back in the early 60s said that if I in this algebra, if I allow myself go to the field of fractions, that in fact it's going to be like differential operators on a fine space. So this certain irrational variety, and so if I go to the field of fraction, that's going to be this algebra has the same field of fraction as this variety. And so that is to say that this algebra is in lambda. And so this you can say is global section of a quantization of a specific quantization with parameter lambda of T star G mod B. So if you have T star of any manifold, is a symplectic variety. Symplectic manifold, you can ask about its quantization. A quantization can be understood in many different ways, but in particular, you'd like to deform the structure sheaf to a sheaf of non-commutative algebras, so that the first order departure from commutativity is given by the Poisson tensor. Right? For cotangent bundles, such a quantization can be achieved not in differentiation theory, but just in fact written down, but just differential operators. And in writing this down, the answer is not unique, because when you deform variety non-commutatively, you should have at least as many parameters as you have for commutative deformations. I mean, if you think of some deformation space that includes both non-commutative and commutative direction, that certainly once you go non-commutative, that should be just as many choices there as you have, well, at least as many choices as you have for commutative thing. And when you have a cotangent bundle and a line bundle, you can twist the transition function for cotangent bundle by the transition function of the line bundle and make it something called a twisted cotangent bundle, which in this case, so the ordinary cotangent bundle maps by the moment map to the nilpotent cone, whereas the twisted cotangent bundle is going to map to the orbit, to a more general orbit in the dual of Lie algebra. And so that the corresponding non-commutative deformation is when instead of differential operators acting on functions, you have differential operating acting on sections of some line bundle. That clear? So a point is that the interesting non-commutative algebras you can write as so we were talking about that for a long time, but point is that this you can also about that thing you think of this thing this is H naught of a quantization of x, not necessarily so, some other x. So this x on two sides plays slightly different role. Of some x which is also which is of a holomorphic of a simplex resolution. And so there's just one more time. So if you have a non-commutative algebra, you can geometrically think about it. I mean, sometimes you can think of this as a non-commutative algebra. You can try to think of this as a deformation of commutative object. Certainly a fair thing to do. The actual commutative object may be singular, and deformation theory may be somehow unpleasant. However, if the commutative object has a symplectic resolution, what you can do is you can quantize the resolution, which is unambiguous thing, which is very nice, and then take global sections. You get interesting non-commutative algebras. If you apply this to homogeneous spaces, you get various quotients of universal developing. If you apply this to the Hilbert scheme of points, you get something closely related to Chernigov algebras, and so on and so forth. So you get interesting algebras this way. And so in general, if you expect to have now it's somehow quantizations. So simplicity of resolutions is a big business. And there's a lot of people doing it. And in general, you'd like to say the results are different if you quantize it. So if you work in, like, representation theory of semi-simple algebra is very different if you work in characteristic 0 or if you work in positive characteristic. But as somehow, you know, the inside of maybe there's many people here. Many people. But the person I particularly would like to, many people working here. But a particular element of that set is Roma Bezrukavnikov. Who has the realization that if I quantize in characteristic P, which just makes sense. I mean, the differential, the differential operators that, you know, you can define them in characteristic P. You can take global sections, just the same algebraic geometry. That sheds light on again, this is somehow much more powerful than quantizing things in characteristic 0, because, well, I mean, my time's up. But so I was going to say, since I drew this thing here, I apologize, I'm going to say something, and then we'll, I know it's very bad when the last speaker of a long day goes over, but I was somehow, you know, had my mind set on saying this, and I will feel somehow unfulfilled if I don't. And so what? So here's my x. When I quantize in characteristic P, I still need to pick a line bundle, and the line bundle means an integer thing, or maybe a rational. So I have many choices of quantization. So this is an element. The choices of line bundles are roughly like it. You know, it's like roughly like pick x. In here, so I have many choices, and turns out, so I quantize in very large characteristic. And so, but then the algebra I get, it's clear that the actual algebra I get, in the end, what will matter is what these things are mod P. right? If I look at differential operators in a section of some line bundle, that, while of course line bundle is different, but the actual relation between things is only that line bundle mod P. So whatever picture in that peak have will be periodic with period P. And so with periodic with period P, it's going to, so I'm not going to draw that. Just going to draw a very, very fine lattice that's supposed to be peak. And inside that lattice, there'll be some picture, some kind of alcove, which will go. I on purpose will do it, trying to do it periodic, but not some kind of well symmetric. Something like this. Such that the algebras, my global sections of my strip of differential operators, they'll be all Morita equivalent within that alcove, but only derived equivalent between each other. So if I have some quantization x corresponding to lambda, within a certain region in peak, which is you think should be of order p, in some kind of big thing. All of these things are, in fact, Morita equivalent, but between x and this, there's derived equivalence. So there's a dB of the coherent shifts on x is equivalent to dB of modules over these global sections of. And if I want to know, and knowing what this various derived equivalences do on say K theory amounts to being able to compute things like characters of a reducible representation of modules over this algebra. So if you have a good equivalence between modules of this, so then it's saying there's some equivalence between modules on representation of semi-simple Lie algebra and characteristic P, with sheaves on the flag variety, and so on the cotangent of the flag variety. And knowing if you have good enough understanding of this, you'd be able to say what are like the characters for reducible representation, kind of a major object of interest, or object of major interest. And so knowing, for example, it's particularly important to know what this equivalence does on the K groups. And now comes the fact that this object, so the way to think about this is like this. If you think, so if this is now, go back to my quantum differential equation, that was defined in some neighborhood of a point where all q's, so this was in q equals 0. And then there were some coordinates q. In fact, that cone here, the cone I drew, is the effective cone of x. There was my equation here. It was some, and so I can ask about the transport between this q equals 0 point and roughly q equals 1. It's not exactly 1, but sort of 1. And so for 5 minutes over time, the last talk will be 1. So once I get to that, then I'm gonna. So what's the fiber? So this is I'm drawing the picture of like the toric base. I'm drawing the absolute values of Q. So now once I go to the fiber is going to be a torus, and its universal cover is going to be exactly this. So this picture is the universal cover of the fiber, of the toric fiber over that point. So the absolute value of Q. And the transport of this equation from here to some particular, and these are the singularities. These are. So they see this equation has singularities. These singularities happen when q to the alpha. So these planes are the planes q to the alpha equals 1 for alpha root. You agree with that somehow? This is the universal cover of a torus here. And the transport of this equation is is the action of this on the K group with the appropriate identification. That was originally a conjecture of Roma, but now it's how to say, it's in the domain of attraction of things we know somehow. This at the time when Roma made this sort of conjecture, that looked totally out of reach, but in fact it is somehow imminently provable at the moment. It's not a theorem, but it is something very close. For Quirrites, yeah. For T star G mod B, that's a theorem. Yeah. For C star G mod B, the theorem of Cherednik before the whole subject started. Yeah. So anyway, somehow the upshot is that the study of enumerative problem lets you get your hands on things like depends. If you know plenty about representation in finite characteristics, you can learn something about enumerative problem. But typically, we're better equipped to study enumerative problems than to study this. This is somehow from the enumerative side. It's much easier to get here than it is from representation theoretic side. So okay, well, I'm very well, so I'll stop here. Yeah.
Any questions for Andrei? Okay, let's thank Andrei and all the other speakers and the guest organizer.